Thank you very much, John, and thank you all for attending this webinar as part of the ICAM webinar series. It's a real pleasure to have the opportunity to present some aspects of our research, and today I would like to specifically focus on a materials challenge which has to do with the development of 3D structure using 2D nanomaterials. And to illustrate this presentation, I will use examples from the literature as well as examples from our research group's activities. I will try to explain why it's important to build these structures, how they are built, and how we can add functionalities to those structures. And I would like to start with this image, which is a representation of the Dallas skyline. It's a special representation of that skyline since, in fact, it is made out of cards. It contains about 1,060 decks of cards, and it was built in 2007. It's about 8 meters tall, and it is the world record for the tallest freestanding card stacks. So why am I showing you this image? I'm showing you this image because I think it's a very nice example of a 3D structure built from 2D elements. And you can see that by using those 2D elements, we're able to create volume, we're able to create pores, especially if we make the analogy between the rooms of a building and the pores of a material. And we are also able to create surface area, again, if we make the analogy between the walls and windows of a building and the surface area of a material. And high porosity and high surface area are key materials feature for different applications, especially molecular separation and catalysis, two areas that are particularly interesting for our group. So today I would like to show you how we approach our approach to building some sort of house of cards using materials. But in our case, we are interested in house of cards that have features at the nanoscale, so we are using nanomaterials for that. We are interested in the porosity of those structures, unlike in the case here where in fact, even though there is porosity, the end goal is to make a beautiful and impressive structure. We are also interested in functionalizing those pores to target different applications. And of course, we want those structures to be robust, unlike the house of cards here, which is quite fragile because there is no bonds between the different cards. So to illustrate our approach toward this objective, I will follow this outline. First, I will discuss 2D nanomaterials in general. So we will see different examples of those 2D nanomaterials, how they are synthesized, and what type of challenges they faced. Then we will look at how to build 3D structure from 2D materials and why this is important. And we will look here at examples from the literature, looking at how we can build those structures at the macro and meso scales. And then I will be discussing examples from our research work, looking at 3D structure built at the micro scale, either using composite or using boron nitride nanosheets. So before discussing those 2D nanomaterials, I would like to highlight an aspect about nanomaterials. Nanomaterials refer to materials that have at least one dimension smaller than 100 nanometers. And there are a number of ways to classify nanomaterials, and one of those ways is according to their dimensions. So we would talk about 0D, 1D, 2D, and 3D materials, and I will give example of each of those. So for 0D materials, we can have, for instance, nanoclusters, which would be grouping of nanoparticles. We have also quantum dots, and we have, for instance, fullerene, which is an example of a carbon-based 0D material. So for each of those different groups, I will try to give an example of a carbon-based material. For the 1D materials, we have, for instance, those nanorods. Here, it's an example of a core and shell type of nanorod that has been functionalized, and those can be used, for instance, for drug delivery. We also have nanofibers. An example of a nanofiber would be cellulose. Nanofiber can be used, for instance, in tissue engineering or in air filtration for the removal of volatile organic compounds. And here is an example of a carbon-based 1D material. For 2D nanomaterials, I will go into more details into those later on, but here are some examples. So for instance, silicate nanoplatelets and graphene. One thing I would like to highlight regarding the 2D materials is the fact that 2D nanomaterials do not necessarily refer to monolayers. In fact, you can have several layers of, for instance, graphene or any other material, as long as that height remains relatively small and you have a high aspect ratio. Regarding 3D materials, we can cite, for instance, metal organic frameworks, abbreviated as MOF, and I will come back to those later on in the presentation. We also have dendrimers, which are those tree-shaped symmetric materials that can be made from polymers, and they can be used, for instance, in drug delivery. And we have here the example of graphite, which is a stack of graphene layers. So looking into more details into 2D nanomaterials, the first and most famous example is probably graphene, which consists solely of carbon atoms arranged in an hexagonal pattern. It exhibits a high electron mobility, high thermal conductivity, and high mechanical strength. When this material is oxidized using strong oxidizing agent, it will form what's called graphene oxide. So you have the graphene layer decorated with oxygen groups at the edges, but also on the surface of the graphene layers. As a result, that material is hydrophilic and can be easily dispersed in polar solvent. Recently, a team at the University of Manchester showed that this type of materials can be used, for instance, as membrane for water desalination. Very similar to graphene, we have boron nitride nanosheets. So in this case, the carbon atoms have been replaced by boron and nitrogen atoms. And as a result, the materials exhibit a higher chemical and thermostability compared to graphene. Very similar to boron nitride nanosheets, we have carbon nitride nanosheet. In that case, the boron atoms have been replaced by carbon atoms, and because of the different types of bonding, we have creation of those regular holes in the structure. Carbon nitride is a metal-free photocatalyst, and I will come back to that material later on in the presentation. Equivalents of graphenes, we have phosphorene and silicene. So those materials exhibit a kind of a bumpy structure. Phosphorene was first produced in 2014. It is a semiconductor. It can potentially be used as a transistor, and it is known to be relatively unstable in the presence of moisture and oxygen. Silicene here also exhibit that bumpy structure, and it is known to have a band gap that can be more easily tuned compared to graphene. Another example of a 2D material is a transition metal dichalcogenides. So in that case, we have a layer of a transition metal, for instance, molybdenum or tungsten, sandwiched between two layers of a chalcogen atoms, so for instance, sulfur, selenium, or tellurium. Those materials exhibit semiconductor properties, and they can be used also as transistor. We have also transition metal oxides and layered double hydroxides. In this case, this is a naturally occurring ionic solid, and we have a cationic layer sandwiched between layers of ions, and those ions can be carbonate ions or hydroxide ions. So all those materials can be easily or relatively easily exfoliated to form 2D materials. So talking about exfoliation and production of those 2D materials, they are typically produced via one of two routes. one that is called a top-down approach and the other one which is called a bottom-up approach. So if I take the example of graphene, there are a number of top-down approaches. All of them or some of them can be used for other types of 2D materials. So in the top-down approach, we start from a bulk material and we start to peel off the layers of, in that case, graphene. There are a number of types of top-down approaches. For instance, we have liquid exfoliation. So in that case, we would disperse the bulk material in a solvent with the appropriate surface energy in order to trigger the exfoliation, and this can be aided, for instance, with sonication. We have also microchemical cleavage, so that would be an example of the Scotch tape method. We have also ball milling and electrochemical or chemical exfoliation. If we take the example of chemical exfoliation, for instance, in that case, we start from graphite, which we oxidize to form graphite oxide. Graphite oxide is hydrophilic, so it can be easily dispersed and exfoliated in polar solvent to form graphene oxide, which can then be reduced to form graphene. The other approach is via a bottom-up approach. So in that case, we start from molecular precursor in order to form those 2D layers. And again, there are a number of different types of bottom-up approaches. We can cite, for instance, chemical vapor deposition, or CVD. In that case, the molecular precursor we deposit or decompose on the surface of a substrate. We have epitaxial growth, where we use a crystalline substrate, and finally we have arc discharge. So all those different techniques would lead to the formation of a 2D materials. But the details or the properties of that 2D materials can slightly differ from one production method to the others. If we take the example of graphene production, you can, for instance, have a different size for the sheet of graphene. You can have different numbers of layers depending on the technique you use, and also different degree of defects. And this is not necessarily an issue, but this needs to be considered when we look at application. If you look at that graph here, when we use CVD, CVD would produce high quality graphene, for instance, and those would be suitable for instance, application in electronics. If we produce graphene from liquid phase exfoliation, those tend to be less high quality, but are still suitable for application in composite, for instance, to enhance the mechanical strength of a given material. So what are the challenges of 2D material? One challenge is probably scale up. Indeed, if we want to use those materials, we want to be able to produce them at scale. So we want to have a high yield, we want to have a high production rate. And if we take the example of graphene, the current production rate of the different techniques I've mentioned is typically below 6 grams per hour, so still quite low. We also have many of those techniques being batch processes, whereas we would prefer a continuous process. There can be product variability, not only between the different production methods, but also within a given production approach. And more importantly, many of the different production methods I have mentioned earlier have not yet been explored for some of the 2D materials I have described before. So in fact, the term challenges is probably not the most appropriate here, and in fact, opportunities would be better suited. Another opportunity, rather than challenge, has to do with the application of those 2D materials. And this is to do with the fact that the industry or the industries that those materials may impact may not yet be fully established or may not even exist yet. So if you look at that graph here. This is a graph that shows the roadmap of biomedical application for graphene, and that was recently reported in a review. And what you can see that many of those applications, such as drug delivery or therastonics, which correspond to the combination of therapy and diagnostic, many of those applications are not fully established and are still under research. So those 2D materials may influence the development of those industries. Another potential challenge of 2D materials is being able to build 3D structure using those 2D materials. Why is it important to do that? It is important if we want to build functional devices which still retain the properties of the 2D material. If I take the example of height or surface area as a property, if I take the example of graphene, graphene has a high theoretical surface area of about 2,600 square meters per gram. If we don't control how those layers of graphene will organize, they will tend to restack and we will lose access to the surface area of that material. So we need to find ways to organize those layers of graphene or other 2D materials in such a way that we can access the surface area and in fact create porosity. And by doing that, we also enhance the access to potential active site that can help, for instance, in catalysis, and we're able this way also to produce materials of low density. By finding methods to build 3D structure from 2D materials, we want to make sure that those methods will lead to tunable structures and also predictable structures. So how do we do that? And I will discuss now different approaches from the literature that show how to build 3D structure from 2D materials at the macro or meso scales. So we have the example of a gelation technique. So here are SEM images of graphene oxide structure with some order at the macro scale. How were those obtained? Well, you have a description of that below. So you start by forming graphene oxides, which then react with glycerol in order to have some binding between the different graphene oxide layers. And then you add resorcinol as a way to trigger cross-linking between the different graphene oxide platelets and form a 3D structure. Another approach is via soft or hard templating. An example of a hard template would be a silica nanoparticle. An example of a soft template would be an oil-water emulsion. And this is what is shown at the bottom here. So in that case, you form a water-oil emulsion, and in the aqueous phase, you disperse graphene oxide material, because as I said before, those are highly hydrophilic, so they disperse very well in water. Then you can freeze the emulsion using via an unidirectional mode, and you can then remove the solvent as a way to get templated graphene oxide structure, which you can then reduce to obtain a graphene 3D structure. Another way is via 3D printing. So you have example of the structure, kind of monolithic structure that can be obtained using 3D printing. In that case, the key part is the ability to form an ink that can be 3D printed. So you can mix, for instance, graphene oxide and silica nanoparticle to form that ink, which can then be 3D printed. Then you would remove the solvent, carbonize the material as a way to go from graphene oxide to graphene, and finally have an etching step as a way to remove the silica component. Another way is via chemical vapor deposition, or CVD. So here you start with the macroporous support, and for that specific study they've used nickel foam. And you want to deposit graphene layers on the surface of that support using CVD. And then, as a final step, you have an etching process where you remove the nickel foam as a way to obtain the graphene network. So all those different techniques enable to have a 3D structure from graphene or graphene oxide at the meso and micro scale. Now I would like to discuss example from our research where we look at building 3D structure at the micro scale and also add a function to those materials. And I will discuss 3 different examples. The first 2 are composites made of a 2D material, so either graphene oxide or carbon nitride nanosheet and metal organic framework. The second type of example will be boron nitride nanosheet that are used to make a porous structure of boron nitride. So we'll look at the first example. But before that, I would like to say a few words about metal organic frameworks or MOFs. So MOFs are made via the assembly between an organic ligand and a metal ion or metal cluster. And they are crystalline porous material. And here's a view when you are actually using molecules, and you can see that you would obtain regular unit like this, and when all those units are assembled, they form this well-defined structure, porous structure. And you can see that by changing the type of ligand or metal, you will obtain different pore size, shape, and chemistry. So we have used metal organic frameworks and graphene oxide to form composites. Those composites were formed via an in situ method, which means that we have first synthesized graphene oxide, and then we have added graphene oxide to the solution of precursors used to synthesize the MOF. And then the MOF synthesis took place. So we used 2 different types of MOF for that. One that is called MOF5 and which is based on zinc, and the other one which is called HKUST1 and which is based on copper. And we obtained 2 different types of structure, and I will explain later on why we think we obtained those 2 different types of structure. But first, we started to characterize the material using different techniques. So you have here the X-ray diffraction patterns for the parent material in the case of the copper MOF, and here you have the composites. The different numbers correspond to different contents of graphene oxide in the composite. The key observation here is to see that the crystalline pattern of the MOF is preserved in the composite, which means that the graphene oxide most likely did not interfere with the growth of the crystal. On the right here, we have an SEM image of one of those composites where we can see a relatively ordered structure. We also look at the porosity of those materials, and here we are making a distinction between the measured porosity, which is in dark gray, and then the porosity calculated for physical mixture of graphene oxide and the MOF, and this is in light gray. And what you can see here is that we have always a higher porosity in our composite compared to the physical mixture. So this means that we have creation of a new pore space, and we think that this pore space is located at the interface between the graphene oxide layers and the MOF's unit. And we will see how we can show that. So here are the thermostability analysis for the different materials. So this is a view of the derivative of the thermogravimetric curve. And in black, we have the curve for graphene oxide. And you can see that there is a peak at 200 degrees C, which corresponds to the decomposition of the epoxy group. And the key observation here is that that peak related to the epoxy group is not present for any of the composite we made, which suggests that the epoxy group in graphene oxide in the composite were involved in interaction with the MOF and most likely with the metallic site of the MOF. In fact, we likely have coordination between the oxygen groups of the graphene oxide and the metallic site of the MOF as shown here. In the case of MOF5, only one type of coordination site exists. However, in the case of HKUST1, two types of coordination site exist, and that's why we think we have a more disordered structure in that case. One thing to note here is that we have creation in those composites of a new porosity, and we will see that this indeed tends to influence the absorption capacity of those materials. Those materials have indeed been used as adsorbent for the removal of toxic compounds or pollutants. So we've looked at the adsorption of ammonia, NO2, and H2S. And again, here we're making a distinction between the adsorption capacity actually measured and the capacity measured for physical mixture. And what you can see from those different graphs is that the composite always perform better than what is predicted for a physical mixture, except for those two samples here. And we attribute this enhancement to the synergistic effect of building those composites and combining the graphene oxide layers and the MOF crystals and creating that new porosity. In that new pore space, we have exposed graphene oxide layers, and those graphene oxide layers are made of dense arrays of atoms, and therefore they should enhance the dispersive forces and favor adsorption. So I would like now to move on to the second type of composite we've made that contain MOF and carbon nitride nanosheet. Here, the goal was to produce multifunctional composite to not only capture CO2, which is a greenhouse gas, but also convert it into chemicals. So here's an overview of the process. In the first step here, we expose the material to CO2, so CO2 is adsorbed, and then we switch to the second step where we provide energy to the system in the form of light to trigger the CO2 conversion and at the same time regenerate our material. For this study, we have used, as I said, composite of carbon nitride nanosheets and metal organic frameworks. And the reason is that the MOF provides the porosity needed to store the CO2 molecule, and the carbon nitride nanosheet provide the photocatalytic activity. The composites here were made in the same way as we've made the GO-MOF composite I mentioned before, which means that the carbon nitride nanosheets were first synthesized and then added to the mixture of precursors used to synthesize the MOF. And then we've looked similarly at different characterization techniques to understand the properties of those materials. So here are the diffraction patterns of the different materials. In particular, here we have the different composites. And the MOF in that case is called Mil and was based on iron. And we have different content of the carbon nitride nanosheets in the system. And what you can see here is that we maintain the crystallinity of the MOF, even though some carbon nitride nanosheets were present. In fact, on the TM images here, you can see the MOF crystal in the composite. The carbon nitride nanosheets are very small and it's hard to detect in those images. We've also looked indeed at the porosity of those materials, and you can see that the surface area of the composite is relatively high. However, it is smaller than what is expected for a physical mixture, which is the second column. And this is different from what was observed with the MOF graphene oxide composite, and we think that this is due to the fact that the carbon nitride nanosheet may affect a little bit the production or the growth of the MOF units and can also potentially block the pores. But the important part is the fact that we maintain or we have some microporosity in those composites, which can be beneficial for adsorption of CO2. So we then looked at the photocatalytic performance of those materials, and to do that, we perform photodegradation tests of a dye. So here is a curve showing the degradation of the dye as a function of time. In black and red, you can see the performance without the catalyst or without light. And you can see that there is no degradation in both cases. However, when the catalyst is present and light is present, which are the blue and green curve, we do have degradation, which indicate that our composite indeed perform as photocatalysts. And you can see that when hydrogen peroxide is present, which is the green curve, compared to the blue curve where there is no hydrogen peroxide, we have an enhanced performance. So this tells us a little bit about the mechanism of degradation and the fact that in that case the photocatalyst probably trigger the formation of an OH radical that can then degrade the dye. If we look at the graph on the right side, so we have here comparison of the performance between the parent material in gray and black and the composite performance. And we can see that all composites perform better than the parent materials. And also we note that the best composite is the one that contains 1% of carbon nitride nanosheet, and it performs better than the composite prepared by a physical mixture method that contains the same amount of carbon nitride nanosheet. So the intimate mixture between the carbon nitride nanosheet and the MOF likely influence the process. So two questions here. Why does the composite perform better than the parent materials, and why do the composite perform better than their corresponding physical mixture? To answer those questions, we looked at the photoluminescence spectroscopy, and which are shown, so the spectra are shown here. So in that case, we excite the material at 395 nanometer, and we look at the emission spectra. So this is what is shown here. And what's interesting is what's on the graph on the right. So we are looking here at the emission peak from the MOF in black and the different composites. And what you can see is that the intensity of that peak is higher for the MOF compared to the different composite. And this indicates that there is a lower electron hole recombination rate for the composite compared to the MOF, which is a positive thing. And also you can see that the recombination rate is lower for the composite prepared by an in situ method compared to those prepared by a physical mixture, which is the purple curve. So again, this is a sign that that intimate mixing produced via the in situ synthesis is key in enhancing the performance of those materials. So then we wanted to understand the mechanism of the photocatalytic property of those materials. So to do that, we needed to know the band structure of those materials. And we obtained those by first looking at the diffuse reflectance spectra of those materials. So this gave us the band gap for the different materials. And also we used Minkowski analysis in order to find out the band position. So as a result of that, we could build a plot like this, where we can see the valence band and conduction band for both the carbon nitride nanosheets and the MOF component. And in the photocatalytic test, what would happen is we would excite electron from the valence band of the carbon nitride nanosheet to the conduction band of the material. Those electrons can then be transferred to the MOF, so we have electron hole separation, and these electrons can then react with hydrogen peroxide to form the radicals that will trigger the decomposition of the dye. So overall, we have proved that we can make composite of MOF and carbon nitride nanosheets, so building those structures at the microscale. They exhibit a synergistic property in terms of photocatalysis. And what we are currently looking at now is using those type of structure to do CO2 capture and conversion. What I wanted to say, and a few takeaway message from that presentation. The first point, 2D materials have a role to play in the 3D world to build multifunctional device with synergistic properties. We've seen indeed that we can confer some functionality to those different materials, and by building composite of 2D materials with another type of material, we can bring synergistic properties. The control of the structure across scale is key for various applications. I have shown here examples of how we can build those 3D structures at the micro, meso, and micro scale. And finally, I think you can guess from that presentation that materials characterization techniques are crucial in understanding not only the structure, but the reactivity of those materials. So I would like to thank my group members as well as my collaborators, and in particular for that presentation, Josh, Les, Sophia, and Catriona for the work on the boron nitride, Teresa and Barbara for the work on MOF graphene oxide composite, and Jindwi for the work on MOF carbon nitride nanosheets. I would like to thank our speakers, and I would like to thank you all for your attention. I'll be happy to take any questions.